Hello everyone, my name is Jiang Changwu from Nanjing University. Today, I'm gonna introduce our work on compiler testing, which is called boosting compiler testing while emulating test programs with long execution time. Compiler is the most fundamental infrastructure in software development. As a cornerstone of software development, the generation of any executable software is inseparable from the basic support of the compiler. Buggy compiler can generate incorrect programs that may cause software to run incorrectly, even with catastrophic consequences. Ensuring the correctness of compiler is crucially important. One common compiler testing practice uses a random program generator to generate a huge number of test programs to stress test compilers. Each of the test programs will be compiled to different executables at different optimization levels and then waiting for output. Their outputs will be compared against each other to differentially test compilers. This is one of the most commonly used compiler testing technique, different optimization levels, also known as DOL. However, the execution time of different programs varies a lot. Some programs take a long time to execute, and some executables end in a short time. Therefore, in practice, developers often set a timeout to control the execution of test programs. Nevertheless, it's still unclear which timeout setting is more suitable for compiler testing. Existing compiler testing techniques have significantly improved the reliability of compilers as they have found thousands of bugs for the most widely used compiler. If an executable running out of time within the timeout setting, it will be directly killed. For example, we set a timeout of 5 seconds, and if the executable does not finish after 5 seconds of running, we eliminate it. However, they use different timeout settings to control the execution of test programs due to lacking sufficient investigation. Sysmith generates random C programs that statically and dynamically conform to the C99 standard. It chooses 5 seconds as timeout setting for executable. C2V detects bugs in code coverage tools by random differential testing. It chooses 10 seconds as the timeout setting for executable. HiCount uses historic data to generate more diverse programs for compiler testing. It chooses 60 seconds as the timeout setting for executable. Yargem produces correct runnable C or C++ and DPC++ programs. It chooses 300 seconds as the timeout setting for executable. To have a better understanding of the impact of different timeout settings for compiler testing, we first conduct a preliminary investigation on the execution time distribution on 30,000 test programs generated by Sysmith. Sysmith is a widely used C test program generation tool, and it is not required to provide test inputs for these test programs. Specifically, we choose GCC 4.4.0 as subject to compile these programs into executables with O0 option. Next, we run each executable and collect its execution time. This is the first empirical study of timeout setting in compiler testing. This figure shows the distribution of execution time. We can observe that although 88% of test programs execute in less than 0.1 seconds. 12% of test programs take longer than 300 seconds to execute. We also noticed that there are very few test programs with execution times between 0.1 and 300 seconds. This may be due to the insufficient diversity of test programs generated by systems and the small number of generated test programs. The gap may be reduced if more diverse test programs are generated. For further investigation, we evaluate the impact of different timeout settings on detecting bugs for GCC 4.4.0 by using the test programs generated by systems. Based on previous results, we add 0.1 seconds as the comparison settings. The testing period is 12 hours, and we employ the DOL testing technique. This figure shows the number of bugs found for GCC 4.4.0 under different timeout settings. In general, as the value of timeout increases, fewer numbers of bugs are found. We also analyze the time spent for each timeout setting to find top 1, top 2, top 5, and top 10 bugs. The DOL 0.1 column represents the time spent detecting bugs by DOL using 0.1 timeout setting. The same goes for the other columns. DOL 0.1 spent less time on detecting top 1, top 2, top 5, and top 10 bugs than other approaches, and also find the most number of bugs than other approaches. An appropriate timeout setting can help improve the efficiency of compiler testing. In this study, we call the program corresponding to executable that requires long time for execution, or even never terminating at all, as a long execution time LET test program. Sometimes the LET test program is annoying. If we can accurately identify such LET test program in advance during the testing process, the testing efficiency can be further improved. Now I'm going to show you the code segments generated by systems. Let's redefine a variable p with short type. Like 5 is a for loop. P gets the return value from the full function. However, the type of return value from full is defined as unsigned char. As the minimum value of unsigned char is 0, P will be always larger than or equal to 0. As a result, the loop condition will be always satisfied. This is a huge loop. It makes the program become a LET program. Motivated by that, we propose elect, the first technique to eliminate test programs with long execution time for compiler testing. Elect is aimed to identify LET test programs and eliminate it for boosting compiler testing. This is overview of elect. First, we get program P from the code generator. The instrumental will modify program P. After being instrumented, we have the program Q. Then we feed Q to the compiler with O0 option, setting a very short running time for executable. If the executable is normally ended, we will get result R0. If it is still running, we should dump the coverage of the running executable, and then use the detector to check the coverage to find out whether Q is a LET program. If it is, eliminate Q, otherwise we will wait for E0 to get the result. After getting the result, we then feed Q to the compiler with other options such as O1, O3, and so on. Notice that this is the rest part of DOL. In this study, all test programs we use are generated by C. Smith and Yargen. Besides, we use the default option of the code generators, which allows us to obtain diverse test programs at random. We use 2 versions of GCC compilers and 2 versions of LLVM compilers as our subject compilers. We choose this old release rather than the latest release since they released for a long time and thus most bugs have been exposed. Each test period is 12 hours, and the compiler testing process runs in parallel with 25 processes during each testing period. This is more in line with the real testing scenario. We choose DOL with timer setting 0.01 seconds, 0.1 seconds, and 5 seconds as a baseline. They are abbreviated as T0.01, T0.1, T5. The conversion approach are elect with timer setting 0.01 seconds and 0.1 seconds. They are abbreviated as elect 0.01, elect 0.1. For example, if elect choose the 0.1 seconds timer setting, elect would wait for the executable to run for 0.1 seconds. If the executable is not finished running, IET will obtain its coverage at the current state, and then find out whether it is a IET program or not by coverage. We adopt creating commits to identify the number of detected bugs from a set of failing test programs. For any test program that triggers a bug, the creating commits checks subsequent commits of the compiler and determine whether commits corrects the bug. If 2 failing test programs have the same creating commits, they are regarded as triggering the same bug. We mainly consider 3 research questions. First, can elect detect more bugs than the baselines? Second, does elect spend less time in detecting the same bug than the baselines? Third, how different timeout setting in elect affect its ability in detecting bugs? As for question 1, this is a detection result of bugs. For example, for the C. Smith result, the number in T5 colon and GCC 4.4.0 row is 25. It means T5 found 25 bugs in GCC 4.4.0 during the 20 hours testing period by using test program generated by C. Smith. Elect detects the most number of bugs. As for question 2, this table shows the time spent on detecting each bug by using C. Smith. The bug column in table refers to each bug. 1 refers to the first bug found by using C. Smith. 2 refers to the second bug found by using C. Smith, and so on. It is worth noting that each bug is unique and does not intersect with other bugs in each project. The T0.01 colon represents the time spent on detecting each bug by T0.01. The same goes for the other colon. It spends less time than the baseline in detecting some bugs. There is a different performance between LLVM and GCC. We summarize the reason is the release time of the LLVM subjects is about 5 years later than GCC subject. Thus, these LLVM subjects should have fewer bugs than those GCC subjects. This table shows the time spent on detecting each bug by using Yargen. It spends less time than the baseline in detecting more than half the number of bugs. As for question 3, elect 0.01 detects all bugs in no more time than elect 0.1. Now I'm gonna talk about the effectiveness of ELECT. For the number of detected bugs, ELECT can find up to 19.8% more bugs than the baseline. For the time spent on detecting bugs, ELECT can save up to 37.69% more time than the baseline. However, there are not much difference in the result of ELECT 0.01 and T0.1. ELECT 0.1 just took less time than T0.1. In conclusion, we first conduct an empirical study to evaluate the impact of different timeout settings on the effectiveness and efficiency of compiler testing. We found that the time used in previous work seriously affects the efficiency of the testing process. Then, we introduced a new concept of long execution time test programs in compiler testing. Last, we proposed the first simple but effective technique named ELECT to identify LET test programs for boosting compiler testing. Our evaluation on the old versions of GCC and ALVM have demonstrated that ELECT can improve the efficiency of existing compiler testing techniques in random testing scenario. If you have any questions or comments, please feel free to contact me. Thank you for listening.